So I want to work through another example here to show you. So again, we're looking at the domain. So the domains are the possible x values. So domain x values looking horizontally. We always start from the left to the right. We want to figure out what's our smallest x value we could possibly have. What's our largest x value we can possibly have. Now, again, as we look here, we do have arrows that tells us that our function is continuing on outside of our picture. So since it's going there to the left, that means it doesn't ever have a definite starting point. So that means our smallest x value we could possibly have is there at negative infinity. And since it's continuing up and to the right here, again, the arrows shows us it's continuing outside of the picture. That means it's not ending in that direction as well. So our x values will also be going into positive infinity. So that's our interval notation as an inequality. It's going to look like this. Remember, if we're talking about infinity or negative infinity, we can never reach it, so we can never include it. Now, again, range, here's the y values. So we look from the bottom to the top. Where are our y values? So as we look from the bottom to the top, okay, the first spot it's hitting, that doesn't actually hit because we have what's called an asymptote here at 0. Asymptote, it's getting closer and closer to that line, but it never actually hits it. So 0 is the smallest y value we have, but it doesn't actually hit it, so we can't include that value. And then as we continue looking vertically up, again, we've got those arrows up here showing us it's continuing on forever up into positive infinity. So this is our range, our possible y values that exist. They exist from 0 to infinity. If we want to write that as an interval, we could say y is greater than 0. 0 is the smallest, and we go up into positive infinity. And behavior, again, we always use this notation. Those are the two places we look. We always look as x approaches positive infinity. So as we look to the right, as our graph looks to the right, what are the y values doing? As we look to the right, our y values are going up, up, up into positive infinity. Versus as we look to the left on our graph here, as we look to the left, what are the y values doing? Well, they are approaching 0. They're always going down to 0. Where that asymptote is, they look like they're going to that 0 value. They're not going any further down than 0. So that's our end behavior there. That's where they look like they're going. So we're going to continue moving on and look and see what happens when we restrict a domain. So this is our function here. It's just a linear function. We've restricted our domain from -4 to 4. So since we have our function, it's a linear function. It's going to be a line segment. Since this is our domain, these are our x values. So then to find the y values that go along with it, we'll plug them in. So we'd say f of 4, that means I'm looking to see what happens in my function when my input is 4, is equal to 3/4 of my input 4 plus 2. Well, 3/4 of 4 is just 3 plus 2. So that means f of 4, when my input of 4 is 4, my output is 5. So I have the coordinate 4, 5. And then you can do a similar thing there with the -4, the lower bound, to find then that your range would be from -1 to 5. So let's continue, see what else we got here. Modeling. Okay, so modeling, we usually use a distance, rate, time standard formula. So whenever you're thinking about a rate, you're always thinking about a distance over time. So something like miles per hour or inches per minute, something like that. So this specifically says she jogs at a rate of 1 mile every 10 minutes. For a total of 40 minutes, this is representing your domain, the max x values that you hit. So it gives her rate is 0.1 miles per minute, because it's 1 mile every 10 minutes. 1 over 10 gives you 0.1. So her distance is modeled by the function d equals 0.1 t. That's our time, our input. So then since she jogs for 40 minutes, the domain is the interval 0 to 40. So to find the range, to find this range, we take our domain, our inputs, and input them into the function. So you would take d of 0 to see what's happening at the beginning. So you take 0.1 with an input of 0, and you take d of 40 to find out what's happening at that 40-minute mark, and that gives you then your function. Let's see. Okay, so here's a different one so that we can take a look at. So while standing on a moving walkway at an airport, you're carried forward 25 feet every 15 seconds for 1 minute. Write a function that models the situation. So again, keep in your mind, it's going to be a distance, rate, time based. So when we think about the rate portion, it's when you see a distance over time. So our rate, so this is 25 feet per 15 seconds, which we can reduce then to 5 feet per 3 seconds. So that's going to be our rate. Our input is time. Our time there is 1 minute, so that's giving us our maximum amount of time. So that means our domain is going to be from 0 to 1 minute, but if you notice here, our rate is in seconds. So that means our domain is going to be here from 0 to 60. And our function, d of t, is going to be our rate, 5/3, times our input of t. So once we know this is our domain, 0 to 60, to find our range, we'll plug those values into our function. So we'll take d of 0, so 5/3 times 0, which is, of course is 0, and d of 60, which means we take 5/3 of 60, which turns out to be, let's see, what do we got, 100. So that means at time 0, it hasn't gone anywhere, at 0, and then at time 60 seconds, we've traveled 100 feet. And so then your range would be from 0 to 100. And I think that's just about it for this section. If I can stop the video.